the next presentation, which is
Yes.
also about modeling, but also using some more advanced techniques to see how you can use it by. So it's by Mostafa Salah, and
Yes.
he's working at IHE. So please go ahead.
Yes. Can you hear me? Well,
Yes, I can hear you.
yeah. Thank you. Um, I'm Mustafa Saleh. I'm a master student at IHE Delft. I will be introducing implementing ensemble Kalman filter on the coastline evolution model ShorelineS. This is the agenda, and I need to introduce two main things. First, the ShorelineS main features, which is the free formation of the coastline, the introduction of upwind approach by Ashton, and the barrier overwash, merging and splitting lakes and islands, and the treatment of groins. The main equation governing ShorelineS is the conservation equation of sediments, and there are four options to use in the transport equation: Circ 1, 2, 3, and Camphius. There are a lot of case studies implemented using ShorelineS, for example the sand engine and the Erie Lake spit development. I need to introduce also the data assimilation, which is generally using the observation data in enhancing the model state and parameters that will be with different weights based on how much you trust the observation and the model outputs. There are two main types for the data assimilation: variational methods and sequential methods, which we are going to focus in this study. The problem is the uncertainties in the input data and the model parameter, which lead to the uncertain model results. The reliability of the model state and parameters need to be enhanced, and that can be done using the data assimilation. The simple one-line model first will be used to implement the ensemble Kalman filter and to assess the results of it. Two validation tests were made at one experiment using the synthetic observations in the ensemble Kalman filter application, and the second one is Pillner consider equation analytical equations. The solution will be used as well as observation for the process. The evaluation criteria will be the BSS, the barrier skill score, according to the qualification introduced by Van Rijn. That one experiment showed very good results comparing to the true model. Here we use the synthetic observation in order to get the ensemble Kalman filter results, which was resulted very close to the true model. The BSS value were showing excellent performance of the ensemble Kalman filter model, and the B coefficient, which was used like as an uncertain value in the ensemble Kalman filter model, was successfully adjusted to the one used in the true model. Second test was the Pillner consider equations using as observation. Both the hindcasting and the forecasting stages showed a very successful match with the analytical solution. The B coefficient through time also was adjusted successfully from the uncertain value to the one used in the analytical solution, and the BSS in the ensemble Kalman filter showed excellent performance for the model, comparing to a good performance with the original model before adding the data assimilation. Now, in order to work on ShorelineS, we need first to compare between both models. In the simple model, you can have you're having like fixed grid points, equal number of grid points in all the ensamples, so that you can easily put them in one matrix and get the mean and proceed to the ensemble Kalman filter steps, like calculating the error covariance matrix, etc., and the Kalman gain. In the simple model also we have like fixed spacing between the grid points. On the other hand, the ShorelineS has no fixed grid points number for the ensample. Some of the ensamples have different numbers from the average, so you can't get the mean value out of this, as you can't putting in one matrix. Therefore, you can't directly use the ensemble Kalman filter, which is challenging, and also you don't have fixed spacing between the grid points. So the proposed solution is to use a quasi-transect approach. This approach is you need to choose a transect ensemble out of the ensemble members, and then a guideline will be drawn for each grid point using the previous and after grid point in order to draw the transect perpendicular to it, and then get the intersection between these transects and the ensemble members, and also for the observed coastline intersections. These intersection points coordinate x and y will be used in the state vector alongside with the b coefficient, which is the longshore transport coefficient. However, this didn't solve the problem because in some cases, for example, having lakes and islands, some of the transects were successfully getting the intersection with the ensemble members and some of the observed coastline. However, these some transects need to be extended, rotated, or both extended and rotated. That was added to the model as well, and the observation, the intersection with the observed coastline were successfully stored. Validation tests were made in the ShorelineS, first using the analytical solution of the longshore dispersion of a beach nourishment, using this observed coastline along from 2017 to 2026. The test result showing a successful adjustment of the B coefficient along time. Initially, both models have at 2017 the same coastline. Then the hindcasting phase showed significant, showed successful matching with the analytical solution along time, as well as the forecasting stage. Finally, the sand motor megascale nourishment tests were made as well using the observation from 2011 to 2016 with the wave conditions and model setup. The test results show also successfully adjusted the B coefficient in the model. Initially, all the coastlines were having the same coastline at 2011. The hindcast first data assimilation step at 2013 showed some oscillations in the model results, ensemble Kalman filter results. However, this was fixed along the data assimilation process in 2014 and 2015, as well as a success in the forecast at 2016, showing a very good results. To further analyze these results, a BSS and root mean square for the results showed in the original model before adding the data assimilation, the root mean square error was around 74 and the BSS was showing good performance. However, in the ensemble Kalman filter, the root mean square error reduced to 32 and it showed excellent performance in the BSS value. So to conclude, all the sub-objectives were successfully achieved, as well as the main objective to enhance the reliability and the robustness of the ShorelineS model. Thank you. That's